today, but at the time was sort of state of the art. And using actually a different technology, these are just reaction wheel gyros, the same kind that are used on many spacecraft today to keep things accurately pointed, here just to keep things stable. They're flywheels is basically all they are. And they keep the platform floating like a small spacecraft when suspended on a bungee cord. The question is, where do you suspend the platform from? This is the window we were going to use. We noticed there was this sort of space above it, so we asked Qantas, could we kind of do something like this, drill some holes in your airplane? And they said no, but we came up with the idea of using vacuum suction cups, a low technology, but actually a very good one. These are just pump-up suction cups, stick them on the wall, they work, and you can hang anything from it. We all got onto the airplane, loaded into 3 separate flight management computers, the baseline intercept plan, and away we went for almost a 12,000 kilometer flight, the longest domestic flight in history because it left and came back to the same place in Australia. Beautiful sunrise over the Antarctic. And you can see just when it was at the horizon, actually looking through some cloud. The pilots complained that our flight plan took them looking straight into the sun. You can see them shielding it, and we reminded them, though, it wouldn't be a problem. It's going to go away in a little while. We had beautiful clear skies over the coastal pack ice as we proceeded inland. Our heading alignment maneuver to get us on track for the umbral intercept. 35-degree bank in a 747, which is a really fun thing to do. This is the perspective from on the flight deck. And so throttled up for the totality run, fired up the imaging program. Here's that camera platform being suspended on a single bungee cord behind the pilot's head, which also made him a little bit nervous. And the Umbra approaching from behind the airplane. And it worked. The imaging cameras sequence, everything fired as expected. This is a guiding camera raw image, processed image, a little bit of additional processing for spatial frequency filtering, getting more information out of the corona. And the point of using multiple cameras is to get different information from different regions of the corona. The CCD camera. This is the film cameras we were running, again, all computer controlled, and then later putting these things together with different levels of processing. There's a beautiful image that was done by David Finley and Miloslav Druckmuller from images taken on the aircraft. And so if people ask, can you get good solar eclipse imagery looking out airplane windows, I think the answer is yes. So I'm going to proceed rather quickly here, skipping the rest of these to show you just 2 other things. First, the same technologies were applied 2 years later, modifying the platform for a 32-second eclipse, some call a hybrid eclipse. It was in the middle of the Pacific Ocean. This required a ship, not an airplane, to get to. We were quite worried about clouds, and we were keeping an eye on clouds using remote sensing, but this actually came down to just sitting down with the captain and just watching for cloud as we actually had to move the ship at about 14 knots. Same imaging platform that was used on the aircraft, modified a bit, and hanging here from a luggage trolley that I managed to grab for a week. Very close call. As you see, the sun emerged just before totality, but here's an imaging sequence. This is courtesy of William Whidden, who unfortunately is no longer with us. I collaborated on some of the processing of this with, and what we really wanted here was to see this arc of chromosphere because the moon was so well matched to the sun in its angular diameter. And then, of course, the third contact diamond ring. And one of my interests here was in looking at the interaction between the chromospheric level, the transition layer actually, just above the chromosphere and the very inner corona. So if you take an image of the sun and unwrap it, you actually can see it's too low a contrast here, the interaction between the base of the plumage of the inner coronal region and the prominences themselves. And the last eclipse I want to show you today is 2006. I don't have time to show you every one. Sometimes you don't have to go to such extremes for eclipse chasing. In March 2006, many eclipse chasers opted to go to Libya. We actually opted to go to Turkey. The main reason for that is we identified 6 airfields across the path of totality, so we could relocate if we needed to, if the weather was threatening after that somewhat harrowing chase by ship. So we had an aircraft, there's the airport right there, there's Centerline right there. We could have taken off and actually observed from the air by crossing or going to one of those other airfields. The goal here, if we could stay on the ground, which we did, was time-resolved high dynamic range imaging for looking for high-resolution structures in the corona. The path of the eclipse, actually, though, in this case, was not in the middle of nowhere, but was right on the grounds of a 5-star hotel. I joined Rick Brown and his group there, and it was an amazing place because we set up right on a helipad, gave us a perfect positional reference. The high dynamic range, this is a really heavily saturated and pushed image from the 2003 eclipse. This is a brightness profile. This is just towards the edge of the moon, but it shows you how the brightness drops off as you go out in solar radius. These are in decades, powers of 10. And so there's almost a factor of a 10,000 from the edge of the sun out to about 6 solar radii in the change in brightness. So in order to accommodate that, the method I've adopted over the years is to use 2 cameras, not try to do it in one. To use a high-resolution camera, long focal length, and low film speed. I was still using film back then, but low sensitivity in order to get into the inner regions of the corona, and a wide-field camera to get to the outer part of the corona. And this just shows you when you put 2 cameras together, you really can get a factor of more than 10,000 quite nicely by doing a ramp of exposures, going short exposures to long exposures at mid-eclipse, and another camera offset with different film speeds, sensitivities, and F ratios. So altogether, you get roughly a factor of 29 from the exposure ramp, from the 2 cameras being offset, another factor of 67 from the exposure ramp, which gives you a factor of about 2,000 in exposure time across the eclipse. And then the film has a latitude, just as CCD cameras do, of about an order of magnitude or so. That gives you a factor of 20,000 imaging. And so across 2 different times of the eclipse, near mid-eclipse and near the end of the eclipse, you get pretty much the same sensitivities on 2 different cameras and then can put images together. An automated imaging system, again, built into a piece of luggage to make it friendly for security at airports. Bringing it off to the eclipse site, and we actually operated a 3rd camera by Joel Moskowitz, who's not here today, as an intermediate focal length camera as a backup. Again, all autonomously controlled, so we can watch the eclipse. And you can see the results of the high-resolution camera. These are actually individual images, as you can actually see the moon moving across during the course of this sort of 4-minute-ish eclipse. The outer coronal camera to capture the outer regions of the corona, individual exposures. And finally, this sort of mid-range camera. And when we put all these images together, just from the different cameras, the diamond ring sequence transitioning at second contact, from the chromosphere, second contact series, you can see the details in the inner corona, both at second and third contact. The motion of the moon, which you normally don't perceive visually, but if you look at sort of the relative motion during the course of the eclipse, of course you never see the thing in the middle, which is synthesizing the 2 images together, but it gives you a sense of how much the moon actually moves during the course of a typical total solar eclipse like this, and the mid and outer corona. Brown coming up, he's going to talk about how we use the capabilities for in-flight navigation to extend this eclipse to well beyond what the theoretical roughly 7.5 minute maximum is, to almost 9.5 minutes of totality from clear skies. So the answer to the question that I raised at the beginning, are we eclipse chasers a cult or a culture? I think people in the audience who've done eclipses will agree we'll do just about anything to see an eclipse. We'll go to extremes for building gadgets and contraptions to help us watch eclipses. Does that make us a cult or does that make us a culture? Well, in the true spirit of Moore's law and binary computations, are we a cult or a culture? Putting this thing through a gate, the answer is yes, we are. And there's a recent redefinition of what cult and culture is, and they're self-referential, which is actually sort of interesting to me. Designating a cult defined as designating cultural phenomena with a strong and often enduring appeal to a relatively small audience. Eclipse chasers, as a percentage of the world's population, admittedly, we're a very small percentage. But we all have to go out from here and spread the word, because this is a pathway not only for fulfillment and cultural aspects, but as a jumping point for all the young people in the audience to think about the future of what they want to do. And even if you don't go into science as a profession, this can really get you thinking about the way the universe works. We're not fringe and we are not non-mainstream. So I will disagree with this, and hopefully by the next SED, maybe we can get them to change this definition. So, but it does sound like us. And that's my trip down memory lane. Thank you.